In the KNN algorithm, what happens when higher value of k is used? This is a picture I just copied from the web, and it just shows you what happens when higher values of k is used. You can see that when k is small, your decision boundaries are fractured, and it's very rough, whereas if you increase the k value, it becomes smoother. And this is an example that shows that smaller k values tend to overfit. Now, what overfitting means is that your machine will be doing a fantastic job on your training set, but then once you put it on a test set, it's going to do poorly. So imagine that you have a training set which is not one of these imagine that you have a test set and data from the test set which is not one of these training sets. And let's say that point is over here, somewhere in this red region. Now, that test point is going to be classified as red when k is equal to 1 because the closest point is this red point. And over here, when you increase k to 5, it will be classified as green because if you look at the 5 nearest points, these are 1, 2, 3, 4, and then probably this one or that one, I don't know. So out of the 5 points, if you pick, you see more green points if your test set is somewhere here. So you can kind of think about what's like the better classification if you're doing this as a human. Well, if your test set was somewhere here, you would say, well, there's a red nearby point, but you really don't want to say that it should be red because that's more like an outlier in this data, right? You see that more green points are nearby, so you probably want to classify this point as green. Or maybe over here it seems like that's classified as a blue because if you look for bigger neighborhoods, you actually contain more blue. Okay, so that's the way that k is used for k nearest, and as you can see, it reduces overfitting. Okay, a given data set has 5 items in group 0 and 4 items in group 1. Then a decision tree is being built, and at the root node, it uses some kind of feature. We don't know what it was, but the result is that it split the data into 2 sets. One had 3 items in group 0 and no items in group 1, which means that 3 item will be a leaf node because once it's in that position, we know that everything should be in group 0, so that's our conclusion. But there's another branch that produces the second set, and I guess the second set will have, since 3 items were already in the first set, the second set will have 2 items that are in group 0 and 4 items in group 1. And now the question is, what is the information gain? Now, information gain is the difference of the information, and in class I explained that the information content of a probability distribution is computed by using the entropy, right? So information gain is simply you calculate the entropy before and after, and then you just find the difference. That is what the first node, root node, is going to do. Okay, so let's try to figure out the entropy. Remember that entropy, the formula for entropy is that it's the expectation value of the log. And although the proper formula is that you need the expectation value with log base 2. That's just a little harder to calculate using your calculator. So we'll just stick with ln of p. And for machine learning purposes, it really doesn't make any difference. When you are trying to use entropy to train a machine learning model, it doesn't matter if you're using ln of p or log base 2 of p. That's why there's this comment, use ln instead of log 2 for this calculation. All right, so let's continue. By the way, this should be actually negative ln of p. So this is negative sum of pi ln of pi. That's what it is. Okay, so let's try to compute the entropy of the very first before the root node. So originally you have 5 items in group 0 and 4 items in group 1, which means that the probability that any random choice from these 9 items, that it will be something that belongs in group 0, is 5 out of 9, whereas probability that it will be from group 1 is 4 out of 9. And therefore we calculate this by calculating the sum. So the entropy here would be 5 minus of 5 ninths times ln of 5 ninths. So the formula says probability times ln of the probability. And then plus 4 ninths times ln of 4 ninths. Okay. And we'll just calculate this using the calculator, which will become negative, and there's a negative, so you just make it positive. So let me use a calculator. So we have 5 ninths, and I put 9 twice. Okay, times ln of 5 ninths, and then plus 4 ninths. The reason I'm putting a parenthesis here is because if without it, and if you just multiply it, I'm not so sure if it gets multiplied to the denominator or in the top. So I think it, even without the parenthesis, it'll still be fine, but I'm not so sure. So it's safer to use the parenthesis than being sorry. Okay, so I put this and I see it's 0.68696. 0.68696. Okay, now let's move on to the next layer. So we have 3 items in group 0, none in group 1. Now in that case, you have a probability of x belonging to the group 0 to be 1, and the other case will be it's nothing. Right? So, and if it's nothing, you don't have to include. So you're really just doing entropy of the single value. But what is ln of p? In this formula, when this 1 goes in, we know that ln of 1 is 0, so this is going to be just 0. Okay? So that's something nice to know. So if a probability distribution has p of x equals to value equals to 1, so that means you only have one possible outcome, then the entropy is 0. Okay, so that's a nice thing to know. And then But there's the second set. The second set will have 2 items in group 0 and still 4 items in group 1. So again, it's similar to this case, except that instead of 9 items, you have 6. And the first case is 2 out of 6, and the second case is 4 out of 6. Which is like, this would be 1/3, and the other one is 2/3. Okay, so let's do a similar calculation with that. Parenthesis 1/3, parenthesis times ln of 1/3, and then plus parenthesis 2/3 times ln of 2/3, and that gives us 0.63651. So that gave us entropy equals to 0.63651. Okay. Now, so we have to find the difference between the entropy before and after, but there's another thing we still have to do. See, both of these are the entropy after. And since 0.63651 is entropy of just one case, what you need to do is you have to take the weighted average of the entropies. And this is the same thing as if you were saying that the probability of being in the first set and 0 is, because the entropy is the average of negative ln of p, you just have to take the average of averages again to get the ultimate average. Okay, so let's now take the average, which is the weighted average, and since 3 items belong into the first set and 6 items belong into the second set, you have to take the average using those weights. So 3 times 0 plus, 6 times 0.63651, and then you divide it by 3 plus 6. Okay, so that's going to mean that you have to multiply this quantity here and times 3, and then divide it by 9. Okay, which is times 6 divided by 9. So actually I have to double it. So it should be times 6 divided by 9, and I mistakenly did 3. Okay, so it's 0.42434. Okay, so now you take the difference between these two. So if we add the 0.63651, see, this one is already negative, so if I add them, it will be like subtracting the 2. Oh, not that one, but sorry, should be 0.68696. Okay, so that's the one, and then I enter. 0.2626 is the answer, so A is the answer. Okay, using a data set of maritime college students, we want to build a decision tree for predicting who gets accepted for cadetshipping. One feature set is the number of demerits, and these are the numbers given. Okay, what is the Gini impurity index for the feature demerits? Okay, so for Gini impurity index, you need to just use the formula, which is Gini impurity index is sum of pi times 1 minus pi. And alternatively, you can do 1 minus sum of pi squared. Okay, I'll use this second one. Okay, and we have to calculate the Gini impurity index for each of the 3 cases, and then take the weighted average to get the ultimate Gini impurity index for the entire thing. Okay, so let's try this. For the set for no demerits, we have either probability of x equals yes, gets accepted for cadet shipping under that demerits equal to 0. Is equal, this would be 0.5 because 50% did get accepted. On the other hand, 50% not accepted, so that's what we have. And since we have these two probabilities, the Gini coefficient, I'll just call it G1, that's like 1 minus 0.5 squared minus 0.5 squared. Okay, or I could have let me write it as plus, because that's what the formula says. Okay, so you're supposed to do 1 minus squared. Okay, and that's 1 minus 0.25 minus 0.25, which is 0.5. Okay, so that's the Gini index for the first case. All right, what about the 1 demerits? Well, for 1 demerits, the probability is that 30% get accepted and 70% don't get accepted, and that's going to be Gini coefficient Gini coefficient 2 equals to 1 minus 0.3 squared minus 0.7 squared, which is 1 minus 0.09 minus 0.49, so it's going to be 0.42. Again, if you go to demerits, 2 demerits, only 10% are accepted and 90% are not. So the Gini coefficient in this case would be 1 minus 0.1 squared minus 0.9 squared, so it would be 0.18. Okay, now we just have to calculate the weighted average. Remember that the population is 80, 40, and 20. So 80 are in this group, 20 are in this group, and 40 are in this group and 20 are in this group. So we just take the average, which is 80 times 0.5, 40 times 0.42, and then 20 times 0.18, divided by the sum of the population, 80 plus 40 plus 20. So let's see, it's going to be parenthesis 80 times 0.5 is 40, so let me just put 40, and then plus 40 times 0.42 plus 20 times 0.18, and And then 80 plus 20 plus 40 is 140, so we're going to divide it by 140. Let's see what we get. That's 0.4314. 0.4314 is C. If the Gini impurity index becomes 0, which of the following is false? Well, Gini impurity index will become 0 if you just have 1p, which is 1. So you have 1 minus 1, which will be 0. But I've also explained that that's true for entropy as well. If one of the probability is 1, then entropy will become 0. So entropy and Gini impurity index, they agree when there's only one outcome. Yeah, but they're different for other values of p. But that's true, okay? And if there's only one outcome, there's no more decision to be made. We know what it is. We know the outcome now. So it just becomes the leaf node. And it also means that the set now contains only one of the classes. If you're doing classification using trees, having one outcome means that it's only one of the classes. So that leaves D to be the only possible alternative. So let's put D. Now, which of the algorithm uses Gini index to determine the decision criteria? Well, I don't know what conditional inference trees are, but I do know that it uses something other than the Gini impurity index nor the entropy. So ID3 is the tree algorithm that makes use of the entropy, and C4.5 is an algorithmic improvement over ID3, but it still uses the same entropy. CART is another version of a tree where instead of using the entropy, it uses the Gini index. So it's going to be A. Which of the following is an ensemble learning algorithm? The last two questions are about the random forests, and you just have to know the concept of a random forest. We call it the random forest algorithm because it's made of many different decision trees. The problem with the decision tree is that it's known to be very fickle depending on the training data. If your training data has some outliers, then the decision trees become very dependent on them and it tend to overfit. So random forest was developed to overcome that problem. And the way it overcomes the problem is by doing two things, which are bootstrapping and aggregating. And such a thing is called bagging because of the B from bootstrap and AG from aggregating. So that's why it's called bagging. Bootstrapping means that you don't use all the training data, you just use a sample of the training data. So you have if you have, say, 100 samples as your training set, then you sample 100 training data from the 100 samples, but with replacement. So that means same points can be chosen again. Okay, so you do the bootstrap sampling of the training data, and also you take only the portion of the feature sets. You don't use all the feature sets. You only if the data set, training data set has like, say, 10 features, you only use, say, 7 features or 5 features or something like that. And then you build decision tree from it. And because there are so many different choices of the feature sets and choices of the bootstrapping sampling, you're going to have many, many trees. And they constitute a random forest grown randomly from the bootstrapping algorithm. And now when it's trained, anytime you have a test set, all the trees will make a decision, and it's like a voting system. Whichever has the majority decision, the random forest will decide following the majority decision, and that's called aggregating. Okay, so and such a method, aggregating from different learning algorithms, is called an ensemble learning algorithm. Now you don't really have to stick to random forests. You could, for example, take classification result from a support vector machine and the logistic regression together, and then a few other machine learning algorithms to find aggregated results. That would be an ensemble learning algorithm, although it would be very costly to train all that. But when you're given just a single machine learning algorithm, then among these four choices, the only one that is ensemble learning algorithm by default is B. So it's going to be B. And I kind of already explained this number 30. We do the bagging to reduce overfitting. Decision tree is often decision trees suffer from that. And then it creates machine learning models from bootstrap data and combines the data, yes. And it makes more accurate predictions than single trees, yes. And it's not quicker than to train than a single decision tree because you're trying to work with many trees. So it's not quicker to train, and even to decide, make a decision, it will be slower than a single decision tree.